Hello and welcome back to another episode of Oxford Online Maths Club. My name's James and today I'm joined by Maria.
Hello, hello. I'm a third year music student at New College and I conduct the University Wind Orchestra. I've played loads of things and I'm here to just have fun and attempt to explain some music things through maths.
Brilliant stuff. I met Maria at a New College thing a year and a bit ago. We talked about music and maths. And Maria came on Maths Club last year, so it's your second appearance on the show. Last time round we talked about, oh gosh, what did we talk about last time?
I think I made loads of notes. We definitely talked about discrete Fourier transforms at one point, but I don't think that was our main focus. I think I just got very excited about that.
Yeah, we talked about, I think, chords and notes. We'll have to link people back to the episode. We talked about kind of building things and breaking things down. I want to do more of that again today. We've got more things to build and more things to break down. Hello to people joining in chat as well. If you want to say hello in chat, please do pop over to slido.com/OOMC. That's where we do things like asking how your day was, like on this five-star scale. So as people join Slido, you can let us know how your day's going. Maria, how's your day going?
My day's been lovely, thank you. I went and studied with a friend this afternoon and did some practice, had a tute. It's all been quite under control. I've got a rehearsal later. Every time we've done this, it's been on the Thursday at 5 o'clock at the same time. And then it finishes at 6 and then I have to run to a rehearsal that is from 7 till 10 that I'm conducting. So it's been quite a busy evening, but I enjoy it, so it's all good.
Thanks for coming along again. Yeah, sorry, I'm still.
How's your day been, James?
Oh, thank you for asking. Yeah, I'm having a good day, I think. I've got back and it's one of those ones where everything's happening all at once. I'm keeping one eye on the Slido where, yes, we've got people in the Slido. That is good to see. I like the phrase under control for how your day is going. I might start using that.
But it's so often the days feel out of control, isn't it?
Yeah, it doesn't suggest that you're not up to anything. You're a bit busy, but under control. I like that a lot. Mary in chat says hello and good to see Maria again. So Maria's from here last time. An anonymous person wants to know if I had a haircut. Yeah, you've changed hair since last year as well, right? Or maybe.
Yeah, I mean, I've had a haircut and I've also drastically changed the colour of my hair.
That's
from mousy brown to ginger, so...
Okay, maybe I should do that too. Okay, right. Something for me to consider. They also want to know if we're doing Fourier transforms, which is possibly something we mentioned last time and possibly something we're going to mention this time.
Potentially. Spoilers.
Anything's possible. Right, okay. While people are filing into Slido and checking in live and letting us know how their day's going, I want to do a couple of quick plugs mentioning Promise Europe Summer School, which we're hosting this summer like we usually do. That's a 6-week summer school with loads of maths and, I'm afraid, not much music, or at least not on the syllabus. There's probably some super curricular music going on as well, let's say. But 6-week maths summer school, it comes with a problem set. Well, to apply for it, there's a problem set of hard problems. So I'm using it as a way to point people in the direction of hard problems to think about, so that even if people don't do Promise, then they can say that they had a go at some of the problems. And I also want to do a shout out to Maths Institute, who are sponsors of the Oxford Online Maths Club. Of course, we're filming in the Maths Institute in my office, and also Jane Street, who are sponsoring Maths Club this year again. Right, okay. People in chat are having an okay day. It's kind of 3-star, 4-star, 5-star in that order. Roughly half people having a 5-star day, which is a nice setup nice position to be in. Okay, we're going to launch. I've got a kind of slightly pretentious title for what we're doing. Is this all right? I don't know. I don't always do this. I don't know why I'm doing it now. I thought we were doing synthesis and analysis. We were discussing some stuff beforehand about what's put in this maths and music episode. I think there's 2 ideas that we should talk about generally first. So synthesis, I think, is like making stuff. And analysis kind of literally means breaking stuff or breaking stuff down to find out what it's made of. Am I on? Is this?
Yeah, I think it's a good track. The thing is, they can mean so many things. Like analysis in different ways can be subjective it can be objective, and then a synthesis can be making something, or it can be specifically combining two things together, which I think in at least some ways we are.
Yeah, I think chemists use these words as well. They sort of synthesize compounds, but then I think they also use them like chemical analysis. What's this? So
Yeah.
does music count as a humanities subject? Is this a kind of STEM humanities thing? Or...
It's the sort of the difference between music and musicology. So musicology is the study of music, and that is very much sort of closer to humanities, sociology, but and sometimes psychology as well. But then music as a thing, as musicking, which is a verb. There's a very interesting book about it as a concept, is an art form. But that doesn't mean to say that not everything can be an art form and everything can be humanity, everything can be a science. It's just depending on how you approach it.
Okay, right, good. Yes. You mentioned analysis of sort of other things about subjective analysis that made me think slightly sort of humanities sort of thoughts. Someone in chat says photosynthesis, which has made me thought that photosynthesis is not making light, is it? It's making other stuff with light. So now I'm thinking about what photoanalysis might be. Like, I guess CSI zooming in on details of photos to find out where crimes were done. Good stuff. I think we're going to start with a bit of synthesis, sort of putting together basic things to build stuff, and possibly with the help of some music, and then switch to talking about analysis afterwards. I would like to show them my Desmos thing, if that's okay.
Yes, absolutely. It was very cool. I had a very fun evening messing around on it.
Yes, although awkwardly, I think the current setup for the Desmos is that it makes noises, which people will be able to hear at home, but I think everyone except Maria, sort of, because of the way we've set up Zoom and Desmos. Okay, so people watching at home, here's what we've got. No noises yet, but it's gonna get noisy in a minute. What I've got is three sorts of wave: a sine wave, sine 2x, which, if you know your graph transformations, is a sine wave with half the wavelength, and sine 3x, which, same idea, is a sine wave with a third of the wavelength. And I've got these coefficients A, B, and C out the front with sliders that let me control how much of each of those I have. So if I turn on the A slider, we get to see sine x. There it is. Great stuff. You've maybe met sine x before if you're doing A-level maths, or possibly GCSE maths. No, maybe A-level maths. A-level maths sort of thing, maybe. So that's my first slider. And then my second slider is sine 2x. So if I turn that one on, then we get to see sine 2x, which is this B term in the middle. And my third one is sine 3x, which is this one. My computer is struggling a tiny bit. Two things I'd like to do with these waves. Yeah, one of them is to make music, although music is maybe pushing it for my Desmos abilities, really relying on Maria for music. Two ways I want to do. One of them you've already kind of seen, that the colour of the line changes. I've got this line of Desmos stuff that says RGB for red, green, blue, and it takes arguments for how much red, how much green, and how much blue to put in the colour. So when I turn on these sliders, it changes the colour, but I can also do this thing up here, which plays a note. So it's going to combine together some sound waves, which is a bit like this. Right, there's going to be some noises now. Hopefully they're not too loud. Sorry about this. Here we go. So this is the first one, sine x, which maybe you can hear at home. It is a kind of beeping tone noise. Sine 2x is a higher pitched beeping noise, and sine 3x is even higher. Music theory time, I think. There's some relationship between these three notes. I can't remember what music theory words I'm supposed to say. Between a low, a higher.
As I can't hear them, I can't.
Oh, right, okay. And then the B one sounds like. And then the C one is even higher. Singing with me. I think from sine x to sine 2x, it's like a doubling of frequency.
Yeah, that would make sense. That would be an octave relation.
Right.
So, Yeah, so if you want an example, then it'd be a similar thing to having
Yeah.
low C. And then I divide the string in half and we get... So it's the same note but an octave higher.
Bro, someone in chat's just laughing at my singing. Did you see the face I pulled just before I realised I'd have to go to a higher note? Because something I'd like to understand, by the way, is why does that sound so much better than the Desmos thing? Something we might try and work out during
Well,
this.
that will be potentially to do with the harmonics that are involved, in that sine waves are very, very pure waves, but those aren't natural waves for us to hear. Like, basically nothing that you'll ever hear in your life generally is going to be a sine wave. They're always going to be slightly complicated in one way or another. Even if it's sort of perfectly in tune and like regular, that doesn't mean that it will be a sine wave. So this might sound nicer because it sounds more like what you're used to. It sounds more like things that you've heard in music. It sounds like things that you are used to hearing. It's how our ears work.
Right. So my Desmos thing is currently stuck on being really beepy sine waves that sound pretty bad, possibly even worse than my singing. At least they're very pure, aren't they? They're very sort of they hit the note.
Yes, yeah.
Someone in chat has perfect pitch. They say that in Desmos it went from E to a higher E and then a B.
That would make sense.
So that interval to get from the B slider, which I won't sing again, but for the people listening at home, I will play a little bit of it. To get from that one up to this one is a frequency increase by a factor of like 3/2, because it goes from 2 to 3. It's an increase of 3/2. Welcome to the maths club. That one's famous as well, I think.
Yes, it's the interval of a fifth. So again, if we're using... So the thing about using this maths is that it's actually... There's a very tangible representation of it, which is that we have this entire string that we use, and if you divide it in half each time, then you get these different notes. So we've had that's the fundamental. You divide it in half, you get the octave. And if I try and get around half between here, there you go. So we get the G, which is the fifth above the C. And it's just by basically going to a quarter of the length of the string. And you can keep going and going and going, and it just the intervals get smaller and smaller.
Okay. So you can change the length of the string in some way, and possibly depending on how cellos work, and I might have to actually think about strings in a minute. The relationship between where you split the string and what note you get is what you've got. Somebody asks how many strings in total. I think they're asking about your cello.
Yes, so there are 4 strings, and they are each a fifth apart, so that ratio of 3/2. So we've got C, and G, D, and A. Interestingly, double basses, which often people think is a cello, but it just a lot bigger, are very, very different because they are tuned in fourths, which is a ratio that doesn't come up naturally in the circle of fifths. Oh, sorry, the circle of fifths when I talk in a harmonic series. Sorry, that's what I meant.
Circle of fifths. I think last year, I'm remembering now. Last year you told me about the circle of fifths and trying to build a kind of perfect scale. If you keep going up by a multiple of 3/2 each time.
That was it. Yeah. So it ends up being like an infinite scale.
Yeah, because
not quite infinite.
People should watch the recording of the previous time we went on math.
It very much does resolve.
Yeah. There's a periodic thing that if you try and build it out of powers of 3/2, it doesn't quite work because of irrational numbers. That's a trailer for a different live stream. Also on this channel somewhere. Joe asks a really good question, which is, does this work for non-sinusoidal graphs? So I've just shown you 3 sine waves and they sound rubbish. The thing that I really wanted to do is to add these together, which of course I've got plus signs in Desmos. Desmos can add things. Technically, behind the scenes, for people who care, if you give Desmos a vector in here, then it will take the separate sine waves with the different frequencies and it will add those together. So the thing it's doing for the sound is the same thing that it's doing for the graph, and it's the same thing it's doing for the color. It's adding these things together, synthesis. Which means that if I turn on 2 sliders at the same time, we can do some combination of these sine waves. Right, I had a practice with this. It's like playing a really terrible instrument, like a kind of What is there a name for an instrument that's like those glasses with the? Think about
Oh, I know. There's an Ond Martineau, but that's a much more complicated instrument. But instead of the glasses where you just sort of like there's water in them as well, and you do that. That's just sort of you just call those glasses, I think.
Right. Somebody says, can some wave frequencies break eardrums? I think they're worried about my Desmos sliders, so we should answer that before I start messing around with people's eardrums.
Only at very, very, very high decibels, I think. Otherwise, I think you'll be fine.
And decibels is kind of strength, so around this end with loud noises. But I think I've got the stream set to be not too hard. Inora in chat says glass harmonica. Thank you, Inora.
Thank you, that was it.
That's the one I'm thinking of. Right, okay, I'm going to add two things. Two things are going to happen, well, three really. You're going to get a visual of those two wave shapes being added together. You're going to get some colour, because it'll add together the red and green and blue channels of those waves, and you'll hear something, which is a combination of those sine waves. So trying to do three things at once, let's see. So I turn that on, and we go for that bass fundamental note again. Let's have some of that. But then I'm going to add in some of this. And that should do a kind of combination of lights. And if I do all of these at once, I can make this kind of note that's a combination of all of them. It's not a sine wave. I'm just going to mute that while I talk over it, sorry. It's not a sine wave anymore, it's a combination of sine waves, and it's made this kind of weird shape, which if I just play you a pulse of it, sounds a bit more complicated than just a sine wave. Slightly nicer, I think. I'm going to fiddle with the settings a little bit. Maria, I think you can see the colour and the shape, but not hear the wonderful tone I'm making.
Yes, I can indeed. It's starting to look a bit more familiar to some other things I've been doing some research into.
Right. I'm trying to go for a particular shape on the screen. In synthesizers, there's different waveforms that people work with. And there's one that's like a sawtooth wave, where you make something like the shape like teeth on a saw. I'm trying to make that because I think it sounds good. We're kind of almost there, I think. So by changing the sliders, I can kind of change the particular wave shape. Oh, that looks pretty saw shaped, nice.
I don't think it's a saw you could cut anything with, but it's definitely a recognisable shape.
No, yeah, it's also not a great shade of orangey brown either. I've synthesised something, but I'm not certain I've synthesised something nice. Yeah, so someone in chat says Taylor series, which I want to stress that if you do A-level maths, you meet Taylor series where you add together polynomials, which is good thought, adding together x and x squared and x cubed maybe to build a kind of different shape. These ones are slightly different because, well, same idea perhaps, you're adding together things with coefficients, but these functions are all periodic, which is perhaps useful. Your polynomials are all unbounded, these ones are all bounded and periodic, which is nice. Okay, I had one more I wanted to show them in my synthesizer toolkit. So combining them like this, I think I've eventually got something which sounds all right. If I turn off the B slider, the one for sine 2x, if I bring that down, the colour changes, the shape changes, and I get something like this. I'm going to bring a bit more blue in, make this a bit more purple. This kind of pinkish purple wave that I'd like to listen to, with a bit of this, and a bit of that. There we go, that looks good. That's maybe a bit loud, so I'm going to bring it down. Kind of pinkish purple wave that I think sounds a bit like, I'm going to put it out there, I think it sounds more like a clarinet. Here we go. Maria, for your benefit, the sound sounded just like a clarinet. I know you can't hear the Desmos thing, just like a clarinet. It made a kind of boo kind of noise doing two notes at the same time. Yeah. Is that a thing people? I suppose I was going to say, can you sing two notes at the same time? And as I was thinking it, I sort of remembered that is a thing.
Yeah, you can also play two notes at the same time, even on wind instruments. So they're called multiphonics, and the way they work is actually by using the harmonic series. So I can do them on. I also play trumpet; that's my main instrument. And you have to sing basically in the exact, not quite the exact ratio that you've just made, but the next one above. So in music, we'd call it either an octave or a tenth above. So that's, yeah, and then you sing in parallel with the fundamental that you're playing, and then you get like extra notes in between. It's very cool.
Okay. So there's a technique where you can sing two notes of a given interval, but that's reminded me that when you sing a note or something, you're kind of an instrument in that moment, and probably there's a kind of rich combination of Desmos sliders or combination of amplitudes of different tones, like your cello strings. I have in chat, sounds like a church organ, which is, I think, generous. Thank you. So you make, yeah. And the question I want to address is the overall combination of wave shapes similar to if they were superposed? It's exactly the superposition. I'm just taking A times sine x, which is, in this case, 0.783 times a sine wave, and I'm taking 0.245, a little bit of sine 3x, just adding those together. And if I put some b back in, I'm adding some of that as well. And the observation I want you to have at the moment is just that by moving these sliders to different places, I can make lots of different things that look like different shapes, just with 3 sliders at the moment. That is what my Desmos slider does at the moment. It has three sine waves, and it doesn't sound great. Maria, advice: how can I make this better?
Oh, I'd probably say you'd need more ratios going further up, because I can't think of many instruments that would only have the expression of the fundamental and then 2 extra waves on top. So it's not going to sound like an instrument unless you have a lot more waves going on. You get a very, very wiggly line on the graph.
Right, so I had to stop at 3 because I've run out of colours. And then I went down a rabbit hole of looking up colour theory, because most people are sensitive to effectively 3 sorts of colours of light. You kind of have different cones in your eyes that responds to different frequencies of light. I'm saying most people because it goes actually both ways. If you know someone with colour blindness, it's possible that they're missing the function of one of those cones, and their eyes only responds to sort of 2 of those 3 colours of light. But it goes both ways. There are also people who are sensitive to a 4th colour, which is the sort of ultraviolet, which means that if there's some ultraviolet light out there, they've got sensors for it, and they can see it, which sort of means that they can see other colours that you and I can't see. It's called tetrachromacy, 4 colours. Don't know anyone with that. But if I could do more colours, so if I break the colour part of my Desmos thing and add in more waves, I think it's obvious to people at home how I do that. I'd add in some sine 4x maybe, some sine 5x, and so on and so on. So you do add in other sine waves, and we can talk maths or we can talk music. Maria, maybe you go first. In terms of music, what am I doing if I put in 4 times the frequency, and then 5, and then 6, and then 7, and then 8, and then 9?
Well, is it possible to get up the handy dandy diagram that I sent you of the harmonic series as it is in music?
Yes. It says reconnecting, which is a terrifying thing for it to say. Why wasn't it connected? Yes, this one?
Yes, that one, exactly.
There you go.
So these are all the numbered harmonics, and all of the notes there are just, if you had the hertz, so that's like the cycles per second of a sound wave, they are just, each note is just double the preceding one. So if you're doing the half of a string again, we've got this is actually the notes that are written down as well. You've got the C fundamental, then in half, actually no, that's the other C, then you go to the half again, you get to G, then you get to C again, then you go to E, then G, then that's the B flat, they get so close together up here, it's really hard to get them precise, but you sort of get the idea. You can do the same on a brass instrument as well, although it doesn't work quite as well because the range is slightly smaller, actually quite a lot smaller than on a string instrument. But it's the same principle, that you are just doubling the hertz each time, and then therefore getting these extra notes and these different ratios between each harmonic and the fundamental. The ratio of the note is in relation to like the fundamental note, not to the note beforehand. So when I said that the 4th doesn't appear naturally in a harmonic series. Some people go, oh, but there's a fourth between the third and fourth harmonic because it's the G to C. You're not measuring it from those two notes, you're measuring from the C to the C, so the first to the fourth. This is more sort of music theory than maths, but I hope it...
Well, I can translate. So in maths theory, we would say 4/3 is not a whole number. I'm not really translating the detail of what you said, but just that one point. 4/3 is not a whole number, but it is a ratio of two of the whole numbers. So if people point over here to say, aha, the ratio there is 4/3, well, yeah, okay, but we were talking about integer multiples of the fixed starting point. The integers contain within them multiples of any number you like. So I think you can do the harmonic series. What am I talking about? Yes, if you start at a higher note, if you choose to start at, let's say this C instead. Is that a C? No, that's not a C, James.
C.
Thank you. Right, what I'm going to do is I'm going to circle the multiples of 3, and then you're going to tell me that that's the harmonic series starting on whatever note that was I've circled. Okay, so I think I go up here, and then up here, and then up here, and then this one. I think so. I'm taking every third note. I think I've built, because of multiples, I think that's the harmonic series starting on that first circle note. G.
It is in fact as well, because I have G strings, so I can show you. That says the G here, G again, then it's the D, G again, anyway, and so on. You might hear as well that I caught some of the higher harmonics lower down in the string. That's something weird I can't quite explain, but it's to do with basically that you can divide in a quarter or into quarters either going this way or this way. So you can have that note here. Can't quite find it, hang on. Either way, you can go in either direction because it doesn't matter necessarily which way you're dividing it, as long as you're dividing it into the quarter or into eighths or whatever.
Yeah, nice. Yes. You're reminding me that in the real world there's some sort of complications from the fact that the string that you're playing is not in isolation. It's also attached to a cello, and it can. We have to remember that, right? When you're listening to analysing the sound that you get other stuff going on at the same time. Also, I think really we should be demonstrating this kind of note stuff. If we're talking about a single note, that's kind of like a single frequency. We should be using my awful Desmos thing, right, to just do beeping notes for each of them. That I think this is true when you play the cello, you kind of get all of these, I think.
Yeah, so you might have something called a spectrogram, which is an image that shows you the different harmonics that are present. And that's a very technical way of seeing it, but you can literally see it on the instrument as well. I think it's called sympathetic resonance, is that right? That, for example, if my C string is really in tune, then the G will vibrate as well, even if I'm not touching it. So you will not be able to see this on this camera, but you can, I don't know if you can hear that, but I could also hear the G as well, and I could literally see it vibrating, even though my hand was here. So that's how things don't exist in isolation. It's also how instruments get their resonance, that you're not just blowing air into a tube, it's how that tube is shaped, and you're not just sort of plucking one string or playing on one string, it also is attached to the whole instrument. Every single instrument works pretty much as either a tube that gets longer or shorter, or a string attached to a box that makes it louder. Apart from percussion instruments, but they're special. So.
In terms of synthesis then, so if I want to make something, I'm still thinking about my Desmos slider thing and how I can make it better. You showed me a graph which I think I can understand in terms of a kind of ambitious Desmos project, if you like, for the oboe graph. Yeah. So this is at the top. This one, right? So I need to zoom out. So at the top, this is kind of what we've seen in Desmos. It's a sine wave with, I want you to think of these, people watching home, I want you to think of these red bars as being my Desmos sliders there. It's been turned sideways to fit a whole row of them in, but large bar means slider active, lots of that one. So there's this huge bar at 1 because it's the fundamental first sine wave, loads of it. It just looks like a sine wave. You've seen that one. Down here, Maria, can you tell me what's going on in this second part?
So that is an oboe, so a real wave, not a synthesized wave. And the quality, or the qualia, is a very nice word, way of putting it, of the oboe is it has a very particular sound because of the harmonics that are present. So you can see these bars, which would be the sliders on Desmos in terms of which ones are louder and quieter. Those would change, as in the sound would very much change if you changed where those sliders were. So let's say we made the third one a lot shorter, it wouldn't sound like an oboe anymore. You couldn't do that with the actual instrument, but you could synthesize it. You could make it in Desmos if you wanted to add loads of extra harmonics on top of it. And a spectrogram shows you that very, very obvious difference between different instruments. It's often based on light or color contrast. So you can see exactly how much each instrument changes. So I think, James, if you scroll down, we can see the differences there. Yeah. So these are all different instruments and they have completely different spectrograms. I don't know how well you can read it, but the one on the left, top left, is a violin. The middle left is the top one is a trumpet, and the right on the top is a guitar. So they have such different sounds. And then the non-harmonic instruments below are the percussion. So marimba, which I would not argue is a non-harmonic instrument. It's just a very differently made instrument. In fact, I take great issue with that.
Kind of wooden xylophone, sort of.
Yes, it's got wooden blocks, and they are on top of tubes to amplify them. Everything is just the thing that you hit or play or blow through that is amplified. But it's definitely a very harmonic instrument, because I'm going to the Royal Northern College of Music for my master's, and on my offer holder day, we had this amazing recital of current students, and one of them was a marimba player, and he did this incredible piece. But what I noticed was that when he played the lowest note on the marimba, what I heard most was the upper harmonic, because it's very hard for those low notes to project. And I had to actually think about listening for the lower note, and that could have been a deliberate choice by the composer, the person who wrote the piece, but it's also interesting that you can hear how the instrument works based on the different harmonics you hear. And then after that, there's timpani, which are the very big kettle drums, and they do have a pitch. So again, they are harmonic instruments, but it's just very, very dry as a sound, you'd say, because it's very resonant, but not necessarily very harmonic in terms of having all these extra things going on. And then a gong you'll see as a percussion instrument, but they can see how much is going on there. But there's a lot of stuff in between the harmonics as well. And I can't quite explain that, but there are some very good YouTube videos about bells if you're interested in that kind of physics.
If we find a link, we will put it in the further reading notes, which get posted to the Maths Club website on the day after the stream. Check the Maths Club website down there in the YouTube description somewhere, if you'd like to find.
Also, all of these images are not mine. I do not claim rights to them. I got them from some excellent papers, which will be linked in the wider reading or further reading.
So this is time on this axis, I think. So it's a grid of coloured pixels, where one slice would say at a particular moment, halfway through your violin, or whatever noise violins make, halfway through, you're getting quite a lot of these notes and some higher frequencies, but nicely spaced out. Look at that lovely stuff. And then this trumpet is doing something slightly different. On the guitar, you can see over time the higher frequencies are dying away faster, which gives you kind of character over time as well. The kind of evolution at different moments, you have different combinations, so you can have this kind of sound that evolves over time.
And that actually has very real world practical consequences in either playing in an orchestra or recording, where sometimes the strings will seem like they're late or out of time, and it's just because their instruments speak later, like the core of the sound, that you can see it gets lighter. There's more of the yellow colour in the middle of the graph compared to the beginning. It sort of takes a while to come in, and that is really, really common, that often you have to say to string players you have to anticipate more because your instrument does not have that very direct sound, whereas you look at the marimba and it's immediate. So that's one of the only ones that has, I think it is the only one that has dead time beforehand, and it's to demonstrate just how immediate the sound is. And it's the same with a lot of the percussion, that there's sort of the beginning of the sound is the strongest, it doesn't grow. whereas in other instruments it does.
Yes, marimba. Now, um, if you want to play along with these at home, I'll put a link. I've got an app on my phone. I can't remember where I got it. I mean, I got it from the Play Store probably. I can't remember if I spent money on it. But you can make these. You can do this kind of analysis. This is what it's doing. It's breaking down a sound into its component parts. You can get an app that just sort of does that. So I'm doing it now. This is mostly for Joe in chat, who says, if I talk just right, is it a sine wave? And the answer is that it's always a stack of sine waves. You can get an app that shows you which ones. That's what this is measuring. It's all sine waves, all sine waves always has been. Evolving over time, perhaps, as I make different sounds and different try singing, but it's always just a stack of sine waves.
There's been a really big trend in music recently at the moment, in like popular music, that you all have heard something like this, where you're listening to a song and maybe the intro or something sounds like it's underwater. Like you can very clearly hear the notes and the words, but it sounds like murky, and that is due to something called not quantization, EQing, which is an equalizer. And what that does is that in the production of the song, they get the recording up and they limit the top frequencies. So it means that you lose a lot of the higher harmonics. And so it sounds different, but it's still a human voice. So the fundamentals will be the same, and it will still be the same sort of maybe stack of sine waves, but then some of them are made slightly, they're diminished slightly. And that's how you get that underwater sound.
So there's a sequence there, I think. If you want to do it to someone's voice, then you start by doing analysis to break down Charlie XCX in the studio, what sine waves did she give us? And you break it down to find out what sine waves Charlie XCX was making, and then you choose you can do something to the coefficients. So if you had a way of breaking that down into which sine waves, you can change some of them. You could switch off some of them if you want to do, or distort them, and then do the analysis to glue them back together again, add them all up, and if you do it right, you might end up with Charlie XCX underwater. Wow, brill. I'm aware I sound very out of touch when I try and talk about anything that's currently happening.
I really thought when you said brill that you were going to say brat, and I was really hoping for it.
Yeah, living for it. Right. That's also, by the way, what's going on with... We're on a Zoom call right now. You can't see the edges of the Zoom call. Behind the scenes, how does this work? For voice over internet and also voice on phone lines, they're doing something like this, where they're suppressing some frequencies. So when you have a call, they're not sending literally the sound wave data. They're changing it to just send you the coefficients, send you the coefficients for a packet, which then gets stuck back together again on the other end, and they suppress some frequencies. They choose that so that it sounds good for voice. This is a long story, I'm sorry. But the result of that frequency crunching is why music sounds bad over the phone, or why maybe Maria's cello, the experience we're getting over Zoom is perhaps not quite the same as being in the room. It's being mediated by something that is right now separating out the frequencies, suppressing some of them, and piping it back. That's why if you've been on hold on a phone and it sounded terrible, then at least partly it's because of this sort of analysis, mess with it, synthesis. Yes, right, okay. There's a reference in chat to the TV show Prime Target, which I'm not promoting it, I'm just mentioning it, that it's out there. Apple TV have released a new show called Prime Target about a mathematician. It's very exciting, except the show is 3 out of 5. Okay, right. We had an aim for this, didn't we? Yes. Synthesis, putting things back together again. I think actually this oboe chart is quite good news, right? For my Desmos experiment at home, right? It kind of says, I only really need the first 5. And then these ones are tiny coefficients. They can't matter.
You might then get an equalized oboe. So if you're cutting out the top harmonics, it'll sound like an oboe that's underwater if you do it right.
Brill. Okay, right, yeah, cutting out the top harmonics because of how sound waves move through water. Is that a physics thing? the stream have any more subjects in it. Right, I'm going to do that. I'm going to take those 5 magnitudes, just reading them off the chart. I'm going to put them into my Desmos, adding in some extra things. And while I'm doing that, Maria, could you explain, I mentioned a clarinet at one point, and there's something about closed at one end and the different frequencies and harmonics you get. Is that something that you know about? I sort of mentioned it, but didn't really know what I was talking about.
I'm going to try and find the notes I made about this.
Oh, sorry.
It's alright.
I think it's the kind of pipe organ thing.
Yes. So, I mean, this could be a conversation about many different things. The first thing to say is that timbre, what we use in music quite a lot, is basically the type of sound. It's how you would describe the sound that is given. So, is it a brass instrument? Is it a voice? Is it a string instrument? Is it percussion? The way they sound different, that is the difference in their timbre. And that is determined by the combination of the overtones. I would argue that almost all of the audible overtones are present in every instrument, but the degree to which they are expressed and how emphasized they are is what changes. Whether it's the first and second and fifth harmonic that are really present, such as in the oboe, or whether it's, as you saw on the violin and the trumpet, it's almost all of them in different ways. That is what determines how different it sounds. Then we get into different definitions. So, for example, intonation or tuning is the different ratio between different fundamentals. They sometimes get, so you might think that timbre and intonation might be more related than they are. Yes, often the way that we can tell something is out of tune is because the upper harmonics of 2 different notes are clashing. And what our brain does is that it takes the numerical difference between those 2 all the different harmonics that are clashing, and because it becomes a horrible irrational number and all sorts of things like that, and our brains don't like that, then you end up with something that sounds out of tune. And there was a music theorist called S9ep4, and he wrote a treatise on harmony in the 1720s. So this has been massive. It's been around for a long old time, and he sort of argued that harmony that didn't sound good was where the upper harmonics were either too close together, so that's when things sound like crunchy, or when they were too close together because the fundamentals are too close together, or too close together because they were out of tune. And then I haven't even begun to touch on the pipe organ thing, but unrelated to that, the way that pipe organs work is that they get this huge sound, and they have a really iconic sound, because with every note that you press, you get at least maybe 3 other notes at the same time because of the harmonics, and also because the pipes, like multiple pipes, are activated at the same time. And then composers have used this to their advantage, and it's also why sometimes things on a pipe organ will sound a lot crunchier than they need to, and it's because they have all these clashing upper harmonics.
Love the use of the word crunchy in this context, that music analysis is much more really than breaking things down into sine waves, whatever I say. Someone in chat says they played tuba in high school and their friend played the piccolo, which 2 quite different instruments really.
There are a lot of pieces that make use of a musical joke where it's a duet between the tuba and the piccolo, or tuba and flute. It happens a lot.
Oh, that's lovely, really.
Yeah, it's very sweet,
Even if it's a joke to have the 2 playing together. Right, I've made my synthesizer oboe. What I've done is I've done 1, 2, 3, 4, 5, and I've tried to set the sliders to big numbers, corresponding with tall bars, which let's have one last look at them before we, oh my goodness, experience this. 1, 2, 3, 4, 5. I was a bit surprised the fundamental isn't the loudest on the magnitude spectrum, but then I realised I don't know what loudness means, and I got a bit worried there. Yes.
Also, there's a whole, I'm sure someone's cracked it, but the last I heard, they hadn't. And we don't understand why, when 2 instruments play together, it's not double as loud. Because by that logic, you'd think that a whole section of string instruments would be deafening. But it's not, and we don't know why.
Yeah, there's some sort of perception of loudness thing going on here, isn't there? And
something to do with projection, something to do with timbre, actually, I would argue as well. Because like one very loud trumpet player can obliterate an entire orchestra, and trust me, I would know. I've frequently caused chaos.
You're the trumpet player. It's you.
Yeah,
Going around
unfortunately.
dominating other orchestra sections. Right. Okay. We're gonna have a go at hearing. I feel like we should hear. Have you got an oboe there as well, or?
I have an accordion and I have four different trumpets and I have a tuba, but it's not mine.
Right. Okay. We're gonna hear a synthesized oboe. I think. Um, People in chat letting us know what instruments they play. One of them says triangle is the best instrument, also the best shape. Don't at me. I think I kind of built the shape in the paper. Right,
It
here
looks
it goes.
familiar. It looks good.
Here we go. Here we go. This is going to be awful. That's all I got. Or I can shift the whole pitch of the thing if you want a higher note. That's all I've got. And Maria can't hear it, so you're.
Someone in the chat, please confirm or deny. Does this sound like an oboe?
I'm also miming along. Right, there you go. Yeah, there is some cancellation of the waves. There's all sorts of stuff going on. So this thing is zero at some points and has some sort of interesting peaks and trough structure, which you can build out of. That's all I've done is build together these kind of basic sine waves, add them together, see what happens. You can get loads of stuff. People in the chat are going to let us know about my oboe experience that I've inflicted on people one more time. Is that an oboe? I don't have any time dependence. I can turn it on or turn it off. I guess an oboe. So it's sort of like your marimba. Your marimba on the charts, we can see the marimba just like noise now. I guess an oboe is a bit like that. It's quite a.
I think it has a slightly slower attack, just because a lot of wind instruments do. I think from watching a very good video by a man called David Bruce, composer on YouTube, highly recommend. He was talking about the saxophone, and that actually has some of the sharpest attacks in any wind instrument in the orchestra, and that is because it was designed by a man called Adolf Sax, funnily enough. And he was utterly insane and invented so many things and was an amazing instrument maker. There's some. He was also insane, just in general. Anyway, so
the inventor of the saxophone. The inventor of the saxophone. You're telling me is someone called Adolf Sax.
Yes, he named it after himself.
Okay, and because of the nature of the live stream, I can't actually fact check you live.
I promise.
Okay. You heard it here first. Saxophone's named after Mr. Sax.
Anyway, so...
Right. People in chat, consensus is that they haven't heard an oboe, and still haven't. Right. Unfortunately,
I can neither confirm nor deny. Although one thing I would also say, it depends on if the person with perfect pitch can tell me what pitch is playing, because I can't hear it at all. So
I was switching. I've got 330 hertz, which they.
Okay, so that's fairly low for an oboe.
Oh, right.
So another thing is that what will inform our understanding of timbre is whether we're used to hearing that instrument in that timbre. So, you know, on those like school keyboards where you could like change up, like press a button and it would be like all oboe or all voice or all strings or whatever. And I mean, something that my friends and I used to do because we found it funny was then play in ridiculously low ranges for those instruments because they sound weird. And that's also partly why, to do with the construction of the instrument, that even if the sine wave is the same or the wave is the same, it still won't sound like the instrument. So maybe it sounds more like a bassoon, which has a very similar construction, but is generally lower than the oboe, or like a cor anglais, which is just a much longer oboe and has a very rich tone to it. So if anyone thinks they can hear the difference between those two, then do tell us.
You know, chat was not jumping up and down to tell me that I'd created a cor anglais, but I've checked the paper you showed me. Actually, I didn't spot it the first time, but it had the frequency and it was supposed to be 349. I don't know what note that corresponds to. I can't work it out either, but it's supposed to be 349, which for the benefit of people watching at home sounds like this. There you go. That maybe sounded more oboe-like to me, although I think even an oboe can play lots of different notes. Maybe we're at the low range of an oboe still.
So, I mean, the note that orchestra's tuned to tends to be 440, and that is sort of the bottom end of the middle range of the oboe. and that which is quite comfortable to play in. But that is the lowest thing you tend to hear an oboe playing. So this is still below that.
Do you think I should go all the way up, like 5? And this is getting dangerous, isn't it? Because to be honest, all I've done is. There's people at home probably don't want me to go.
Yes, perhaps not.
Chat say F but weird.
Okay.
Is the kind of I'm emphasising the third harmonic, so believably upper fifth or something from what you might expect me to be doing, but I have messed around with it a bit as well. Okay, right. I made a lovely blue colour as well, which one thing about blue, well, colour in general, I suppose, if you like. We were talking about this just before we went live, so we've come full circle, which is nice. Where am I going? I'm going over here. There we go. No, yes, but over left. It's quite a complicated stream. We've done quite a few things. So analysis, breaking things down. You can do that with colour, famously. So far I've been building up colour, combining together some red and green and blue to make, at first, a horrible brown colour, and then rather nice off blue kind of shade. Don't know, people at home might have more interest in names of colours than me. This is famously something that you can do in the other direction, to take some complicated light and break it down into frequencies that it's built of. This is something you can do with a prism. Imagine Isaac Newton hanging around with prisms and natural light and things splitting up, and then Isaac Newton naming some colours. But it's also something you can do with more high-tech equipment, like the James Webb Telescope. I've stolen a picture from their website. I'm going to link to them as well. I hope this is okay. They pointed a spectrometer at the star Altair. I sometimes feel sorry for astronomers. There's people who study like far-off stars, perhaps, because you don't get a lot from the stars. You kind of only really get light. You get electromagnetic waves from them. You don't get electromagnetic waves and a postcard at Christmas or something. You just get electromagnetic waves. So you've got to analyze. You've got to analyze what you're given. So they have to do things like looking at the light that they're getting. And to me, they all look like little twinkly white dots in the sky, right? But to break that down using the same techniques that you might use to break down a music signal, because it's all just signals. If you break it
Everything
down,
is just Fourier transforms at one point or another.
just do a Fourier transform on the same thing. And it doesn't really matter if you're breaking down a picture of a sine wave, or breaking down the sound of the sound wave, or breaking down the light of the colour that James has associated with the sine wave. It's kind of all, the analysis is the same in each case. They do these kind of plots where they look at what light is missing, because that corresponds to the star being up to something. In this case, I think being made of hydrogen. Not an astronomer. Please go and find out more about astronomy if you want to learn about astronomy facts. Joe in chat says that the synthesized oboe didn't sound a lot like an oboe, but maybe accordion-ish.
Okay, interesting. Because accordions are technically wind instruments for godforsaken reasons. I mean, I do have one right next to me if you'd like a demonstration.
I think this is the closest you're going to get to an invitation to play the accordion on a maths live stream on YouTube.
I mean, what a claim to fame. So this was given to me by my old conductor, because a very good friend of hers very sadly died and had a huge collection of musical instruments, and she said that she wanted it to go to someone who would use it. And guess what? I have been using it. I learned a lot of carols on it over Christmas, and it was great. So yeah, it's a wind instrument because it uses bellows, or rather, so it's got this cavity, as you'll see here, which opens up. In case anyone's never seen an accordion before, this is going to get quite loud quite quickly. I've also put it on upside down. Apologies.
Do I need to turn this down? Also, someone in chat's made an important point about my oboe, which we're going to fix in a minute.
I see. Yes.
I did the oboe wrong.
I see. Right. So.
Oh my goodness.
Let's see. Let's play something nice. Let's play a C major chord, and then we have the buttons here, which you press like that, and then you can also play a C major chord here. But see, I don't really know how this works, I have to be honest. But all I know is that you you have to, otherwise I think it's a vacuum or like close to one. So you have to make sure that air is actually flowing through it. Otherwise it damages the instrument. So it doesn't make a sound if you don't press a button. So hands off, it's moving, but no sound is coming out. Whereas then when you press something, then it makes a sound. So you're releasing the air.
I think the accordion's got that kind of richness of sound that kind of is characteristic, right? It's got lots of, I think on purpose, like the buttons, it's kind of what I recognise as a traditional keyboard down one side. But you've got these buttons on the other side, and they're doing sort of whole chords or whole combinations of notes on the other side.
So the way that these buttons, just a very quick accordion tutorial. So the way that these buttons work is that you have single notes, although even that's an octave, and then you have the major chord, then you have the minor chord, then you have the dominant seventh, and it goes up and down in fifths. And that's how you work out how to play. You really do have to have like a mental map of it, and you really have to understand how fifths work for it to work.
Oh my goodness. We did talk about chords, I think, last time. There's some unmined maths content there as well that people can find out about. The important correction I had was that I went to all this effort of setting up the sliders and did the visual, but I didn't put them in the sound. So people were just listening to the bottom three and not the DE. So I have an updated oboe noise ready for you now. Which I think is a little bit more oboe if I turn these off. That's what we were previously listening to. Bit of a hum. Whereas this I think has got a bit more of a bite to it. I don't know, I associate oboes, because they were next to us. I played clarinet in the past, and the oboes were next to us. I think oboes just, they sound different from clarinets. So for me it's a little bit uncanny valley. There's something wrong with that clarinet. Something that I could maybe I could work out if I looked at the spectrogram. I could point to that's why.
Well, also the reeds are different, so they'll resonate differently. Obviously, in the clarinet you have those like quite big flat reeds, and then with oboes you have these very very thin double. Are they double reeds? No, I'm going insane.
I think it is a double reed on an oboe. Yes.
Yes. Yeah. So they're much thinner, which I think is why you get that very. It feels like a very sort of wishy-washy. Subjective analysis. However, I think you look at the oboe reed and you think of the sound of an oboe, which is quite narrow and nasal and was laser-like. It's why it cuts over an orchestra so well when you're tuning. And you listen to that and you think, yeah, I can imagine that coming from that tiny reed.
If there's any oboe players watching live or watching the recording, then we do love you, really. I'm sorry.
Yes, we very much do. You provide a valuable service.
Marion in chat thinks that my synthesized oboe is slightly better. I guess now it sounds like I'm trying to replace oboe players. I promise I'm not. My synthesizer is nowhere near good enough. Right, we're getting close to 6 o'clock, and you've got to run to conduct an actual orchestra not made of sine waves, although secretly made of sine waves. So we will let you head off. Is there anything else that you want to tell people about music and maths? We can put more stuff in the further reading notes, of course, tomorrow. But
I could talk about music and maths and music and physics for absolutely, genuinely hours, and I really, really hope that people have found something useful from this. There is so much content online, particularly YouTube, where so many people have either done more on the maths side or more on the music side. There are even articles you can get for free without needing the university library permissions. The one thing I'd always say is remember to sort of be critical of things. There are some people who maybe know more about one than the other in terms of more about maths or more about music, and then forget some pretty fundamental things in either direction. So yeah, critical reading is very important, but always be curious, and there's so much to learn. So I hope you enjoy.
I think we might have helped some people with their personal statements, but I don't know. We might have given people an idea for an EPQ. I'm not sure. Well, we'll find out. Let us know. Let us know if you decide. Always let us know if you decide to do an EPQ on something that you've seen on Oxford Online Maths Club. Or just read in the further reading. Right, I'm rambling, which means it's probably time to stop the Oxford Online Maths Club. Chat say thank you very much. So, as always, we say thank you very much. Thank you very much, Maria, on stream. Thank you to people watching at home. Have a good evening, everyone. We'll see you next week for another episode of the Oxford Online Maths Club.
And thank you very much to James as well for hosting.
Yay! I do it every week. Right. Thanks, everyone. How do I switch this off? I think I remember. I think it's this one. Bye.